Thank you everyone for coming to our first ever DeepSpeed meetup. um, I was talking to Tunji, who is our engineering manager today. DeepSpeed is actually 4 years old on GitHub. We open sourced it 4 years ago. Um, we probably should have done this a lot earlier to meet to meet with people, meet with our users, but hey, it's never too late. Also, before today's talk, I want to recognize one person, Yu Xiong, who was the founding mother of DeepSpeed. Yeah, she started DeepSpeed way back, 17, 16 even, long time ago. Sure, more than 4 years ago. Okay, so I'm Martin. I'm the product manager of DeepSpeed. Oh, the spill echo. That's okay. Well, thanks for coming again. Today we have two talks. Tonji, I'll let him introduce himself. And then Taka um, will talk about something else afterwards. I don't. I'm not gonna say the topics, and I don't want to spoil the surprise. Okay, so I guess without further ado, Tanji, do you want to get started?
All right, thanks, Martin. Um, okay, can you hear me all the way back there? Excellent. All right, well, welcome to this is DeepSpeed's very first meetup, and as Martin said, we ought to have done this a long time ago, but I think it's never too late to start something good. So yeah, talk I'm going to give today, I'm just going to focus mainly on the history of DeepSpeed. We do plan to have a lot more meetups, and that will get into a lot more technical details, and hopefully also get some feedback from you guys. This is all part of our, we've benefited a lot from the community, and so we're hoping to sort of give back and engage with the community so we can serve you guys better. Um, so, so what's the story of DeepSpeed? Where did it start from? As Martin mentioned, it wasn't quite 1776. It was just sometime around 2019. So in October 2018, so the language model world was rocked by a release from Google. I'm giving it away, so who knows what it was. It was released in October 2018. What? Yeah, the spoilers of the screen. You're paying attention. Yeah, BERT came out in October 2018, and there was a mad scramble. Anyone who remembers then, there was a mad scramble to try to reproduce the BERT results all over the industry, not just at Microsoft. So here at Microsoft, we're also trying to do the same thing. So early 2019. So what did we have as tools that we could use? This was all so new to us. Well, we had NVIDIA Apex. It was a mixed precision library for data parallelism training. And in terms of compute, we had 64 V100s that were a massive 16 gigabyte memory available. So it's pretty amazing. And then the network was Ethernet, 4 gigabits per second, compared to what you're kind of used today was like 400x, 1000x slower, if you could believe it. Um, and the maximum batch size you could fit then was about 4 per GPU. And so the existing solution that we sort of started with was the NVIDIA Apex. It was using a technique known as gradient accumulation, but they had this, I don't even know, looking back, it seems like such a trivial thing, but then it was such a big thing. They were doing the gradient accumulation and reduction on every micro step. And so the very first thing we did in a tool called DeepScale was to sort of move uh, the gradient updates out of the micro step, out of the loop, right? And this is sort of super trivial right now to look at, but trust me, like 5 years ago, this was a huge deal. Yeah. Oh, gradient accumulation steps. So it's a technique when you don't have your GPU memory is typically not large enough to host the batch size. I think this was like 1,000 batch size, and you could actually fit only 4. So what you do is you just accumulate the gradients over it. So yeah, we kind of claim credit for smart gradient accumulation back then. We had no idea where we were going, but this seemed like a huge step forward. And so we then were able to train through the BERT data set in 8 days, and that was like a major accomplishment. So yeah, said that this is a DeepSpeed meetup. So what's DeepScale? Well, DeepScale is the precursor to DeepSpeed. That was the name we had for it back then when we kind of started out. You can see we were still learning as well. We couldn't even name it properly. So move forward to zero, which I'm sure most people here know about. A lot of people know so much about nothing, right? Zero and deep speed, right? So what's the story there? Well, um, moving ahead, multi-billion. BERT was a massive 300 million parameter model back then. Can you believe that? And it was the state of the art. By this time now, multi-billion parameter models were becoming sort of the norm or becoming the rave. And GPT-2 kind of led the way with 1.5 billion. NVIDIA came out with Megatron, which was 8.3 billion. And the immediate effect of this was that the models could no longer fit in a single GPU, something we took for granted with BERT that could fit in a GPU. And so then I guess the systems folks were super getting excited here now, like, whoa, you can't fit. So what do? We parallelize, and there are all kinds of ways of parallelizing. And so here, the table I have here is the various parallelism techniques that people started exploring then. Data parallelism was well known. That assumes your model fits in the GPU. You have a lot of data. You partition your data across all your GPUs, and you're good. But then if, in the case where the model doesn't fit, what do you do? So we started having techniques like model parallelism, where you're able to split the model across multiple GPUs. But then that has high communication costs and can only be restricted to within a node. And so we came up with something called Zero, which was basically based on the observation that when you do data parallelism, there's essentially replication that's happening across your GPUs. And so we came up with ways of partitioning, so partitioning, deduplicating various model states. And so we did that progressively, starting from the optimizer state to the gradients to the parameters. And so that kind of led to all the 3 stages of zero. So it's not like 3 stages of pain, although they were all progressively harder to implement. We were at least very smart to have named them appropriately. So imagine if we had started out with parameter partitioning first, probably never would have succeeded. So started with the easiest one, optimizer partitioning. It was stage 1. And with that, we were able to actually collaborate with our friends at Turing, our sister team, to train a 17 billion parameter model. And that was the largest model at that point in time. It was a combination of zero and model parallelism, which today we call tensor slicing or tensor parallelism. And it was at this time that we switched from deep scale to deep speed. And yeah, and like Martin said, 4 years ago, we open sourced DeepSpeed, and the rest is history. Since then, DeepSpeed has been used to train a whole lot of models, some of which I will kind of show the list a little bit later on. So the pretty cool thing about DeepSpeed, if you may not have noticed, is that it's a palindrome, and we CS people love palindromes, right? So yeah. Okay, now we can train multi-billion parameter models, 17 billion parameter models. So what do we do next, right? Trillion parameter models, right? Like, what else would you do, right? And so 2020, OpenAI, usually ahead of the crowd, came up with GPT-3, 175 billion parameter. So kind of ask, okay, so what does it take to get to a trillion parameter model? Well, it seemed like 2 major approaches. One is you could do 0-3, which is sort of partition everything across all the GPUs that you can find, or you do something complicated called 3D parallelism. And 3D parallelism basically means partitioning on 3 dimensions. So you have the model partitioning, which is really tensor slicing, which is basically you take every layer, you split it across multiple GPUs. Pipeline parallelism, you share your layers, partition them across different GPUs, and the data parallelism or zero data parallelism. With 3D parallelism, so that means now our table of parallelism techniques is now growing. Right? So add model plus pipeline plus data. And the great thing there, I don't know if I should be calling out names, but Shading over there, so they did a great job of implementing 3D parallelism that it all scaled. Can you imagine that? It scaled linearly as you increase the number of GPUs, and we're able to fit a trillion parameter model on just 800 GPUs. It's pretty amazing. 40 teraflops then was pretty amazing for a V100 in terms of what you could achieve. And so with that, we collaborate with our folks, our friends as well, Turing, and with NVIDIA. We were able to train a Megatron 530B model. It took 2 months and 2,100 GPUs, 270 billion tokens. A couple of years later, the big science project leveraged the same technology to train the Bloom 176 billion. Took 3.5 months, 384 GPUs, over 300 billion tokens. So what do we do next? Continue scaling? No. Well, it turns out that you can't keep scaling, right? Because you end up running out of compute. So let's see why. Megatron 530B, like I said, trained for about 2 months, 300 billion tokens. The reality was that this was a severely undertrained model, because later on we saw people come up with much smaller models that trained on much larger amounts of tokens. So like the Llama 65B, Mosaic ML 7B, they trained on a trillion parameter model. So in reality, the 530B model should have been trained on a trillion tokens, which would have taken between six months to a year. Okay, and so then if we keep scaling at that rate, the 10 trillion parameter model will take you 10 years, which is pretty, ridiculous, right? So because your customer base will probably have moved on to something else by the time you're done. So what do? Well, you keep scaling, but you scale smartly, scale with sparsity. In other words, you increase your model capacity without increasing the compute requirements. And so this is sort of the mixture of expert work. And the plot I'm showing here, the red curve there is showing like a typical dense model, 1.3 billion parameter. The blue curve there is the same dense model, but with 128 experts. So from a compute perspective, it costs the same thing, same amount of time to train. Validation loss, you can see that the model with a mixture of experts is significantly better. The yellow line there is showing a 6.7 billion parameter model, which is 5 times larger. And so what this is showing you is that for 5 times less the cost, you could use mixture of experts to achieve the same model quality. And so, yeah, we released DeepSpeed MOE, multi-trillion parameter training, without, the corresponding increased scaling of compute costs. And this had excellent efficiency. So so then we sort of branched out a little bit to democratization, right? It's all great and well training all these massive models, and costs a lot of money. So who's going to use them, right? Fine tuning, right, is sort of like how your customers sort of take your massive model and sort of adapt it to their scenario. Well, it's really too expensive to fine tune, then no one's going to use it, right? If it's too expensive. So like the GPT-3 would have required like 256 V100 GPUs to fine tune. Not so many people have access to that kind of GPU resource. And so we sort of took a step back and said, what's the problem here? The model cannot fit in GPU. That's the problem. Well, let's look at a typical server machine. Realize there that there are multiple hierarchies of memory there, right? So the HBM GPU memory is actually the smallest. So in DGX2, it's there it's like half a terabyte, whereas you have their CPU memory of about a terabyte and a half, and then you have like 30 terabytes of NVMe. So how can we leverage all of this in order to train and fine tune? And we observed that if we could leverage all of this, then we could actually fine tune a trillion parameter model on a single node, and 32 trillion parameter model on 32 nodes. But the challenge is the bandwidth, right? So if you're going to be fetching your model from NVMe, then you have to sort of go through PCIe. You don't have access to the high bandwidth HBM memory anymore. And so the solution to that was to basically rethink how we do the partitioning of our parameters. So now we partition each layer across the multiple GPUs, so that when a layer is being fetched into memory, you're actually leveraging all the PCI links across all the machines that you're using. And we have a very fast NVMe library that's able to basically get 95% of the peak of the NVMe. And so in reality, we're able to achieve about 25 gigabytes per second of IO per node, and that scales linearly. So as you add more nodes, you're linearly scaling. And so with that, we're able to realistically fine tune, 100 billion parameter model on a single node or on a few nodes. And then we took a detour after that to application space, and we released something called DeepSpeed Chats. And DeepSpeed Chat here is basically leveraging RLHF for training. And this was a fun project, I'll say, because this for us involved, designing an application side and also rethinking the DeepSpeed engine to be, in particular, be able to support both training and inference and token generation happening in the exact same workload. Because previously we've always thought about these things as being separate. You do training, you do inference, all separately, but here we ended up doing all three together. And so we redesigned our DeepSpeed engine to be a hybrid engine, and that allowed us to, achieve some major improvements over the state of the art. So for example, we're 15 times faster than the state of the art, and we could support models that were 7 times larger than the state of the art by basically using zero and parameter efficient techniques like LoRa. So then we now get to inference, and so this is sort of like, I guess, where the wave where we are right now. A lot of models have been trained, and people now want to use them. And so how do we? So we decided to look into how can we help our customers, our users, to inference the models they've trained with DeepSpeed. And the way we looked at it was to look at the entire landscape of the inference workload. And we recognized three different spaces. First was a single GPU, models that could be inferenced on a single GPU. And for that, we designed very efficient kernels because all you care about then is just how fast can you compute. And then there are models that are much larger, like the Blooms that require multiple GPUs. And so for that, we designed techniques for basically parallelizing them across GPUs, tensor parallelism in particular, to get high performance. And so something like the Megatron Turing half a trillion parameter model could be inferenced there. And then finally, we looked at the MOE because as we believe that's sort of the right way to scale model capacity going forward. And we designed optimizations there where for a trillion parameter MOE, we could actually inference it on under 25 milliseconds. But at the same time, we did not forget our democratization story. And so, for folks who couldn't afford, who wanted to inference like a 100 billion parameter model on a single GPU, we designed something called zero inference, which is essentially similar to a zero infinity, where you host the model in your NVMe and you stream it in for inference as you require. And this allows you to scale up the batch size so that you can get high throughput, even though you're inferencing from NVMe. So based on that, we built a service called DeepSpeed MII to sort of power DeepSpeed inference. So DeepSpeed MII packs in a class of optimizations that applies to a large range of models. And in particular, I think the last count was about we could optimize about 24,000 different models, from a family of models out there. And we achieved in terms of on Azure, we could see improvements, orders of magnitude improvements for inferencing. And this, of course, translates into cost savings, which customers really care about a lot. And for the MII, we had, basically two APIs. One was for deploying the model, and then the sort of the client side of things for how to, run inference against the server. Model implementations. Forget the last I. Who can help? Sorry? Sorry? Model inference and implementations, I think. Yeah, that's right. Yeah, and so we kind of call this DeepSpeed V1, inference V1. So we learned a lot from that experience, and now we sort of transition into the inference in what we call V2, and that's sort of where we are right now in terms of like the most recent work we did. So here with the V2, we're certainly doing a lot better job in terms of the engineering and thinking about the design. So We're introducing a lot of modularity, and I'll go to that in a second to talk about the design. But one thing to just point out here is that the fast gen is sort of the collection of all of this new design that we have, and this is something that's available both in the open source and on Azure ML. And so with FastGen, we went with a more modular design where we wanted to be able to take advantage of existing solutions that were out there, so we didn't have to recreate them, leverage existing solutions we had, and then just optimize when we needed to. And particularly here, there's been a lot of work in this space recently with things like the blocked KV cache or page detention work from VLLM. There's been a lot of interest here. And our most recent release, we were able to, I think, at least at this point, still be the state of the art in terms of token generation. And here, this is a fairly easy to use technique solution. And so yeah, I'll just talk a little bit about the results. For most recent results, this is showing throughput latency analysis comparing against VLLM. The y-axis is latency, x-axis is throughput. We're looking at scaling the clients up to 32, so as you increase the number of clients, you put more load on the system, your throughput goes up, but the latency also kind of goes up. And what you can see here, the blue curve being FastGen, is that we're able to maintain a much better result compared to VLLM. And the key reason is because we have this technique called split fuse, dynamic split fuse, where unlike VLLM, which will have to stop token generation when a new request comes in, we are able to automatically combine a prompt processing, like a new request coming in, with the existing token generation. And that allows us to have much better latency as we increase our throughput. Yes, please. Latency milliseconds, yes. And so along the lines of, I think here, trying to define what's sort of the right metrics here. So we define something called effective throughput, and by that we mean like, what are as you scale up your clients, the number of clients, the load on the system, how many of your requests are actually able to meet a target SLA, right? And that's what we call the effective throughput. And you can see here that unlike VLLM, mainly because they have to stall generation whenever a new request comes in, their effective throughput drops, while we're able to maintain a much higher one. Yep. And so that's most of the technical part that I'm just going to go over. Like I said, in future we'll have more detailed description, talk about all of these techniques. But the one thing that I'm also very proud about in DeepSpeed, and I think it's probably as important to the success as much as the technology, is that DeepSpeed is actually very easy to use. And early on, we really made a conscious decision here to make it easy for users to basically integrate DeepSpeed into their pipeline. Like we wanted that to be like, I think we used to have slides about how in four lines you could integrate DeepSpeed and go from training on a single GPU to training on 1,000 GPU just with 4 lines. And a key part about that is the idea of using configuration, DeepSpeed config file to control DeepSpeed engine rather than putting things on the command line. And so that's sort of what I'm showing here. DeepSpeed config is basically how you configure the DeepSpeed engine to your need. And you, in terms of your modeling code, you just change a few lines. And this design has stood the test of time. I don't know like what kind of models will be trained in future, but I'm very proud of this actually. Yeah, so for all of that, let's sort of just step back again. So what's been the impact? I try to summarize this here. I hope I catch all the nuances that are needed. In terms of all massive models that have been trained out there outside, that we know of, they've mainly been trained by using DeepSpeed. And so you can see here a variety of companies, including Microsoft and non-Microsoft, they've all used DeepSpeed for training them. In terms of frameworks that are your favorite frameworks, PyTorch frameworks, they all have DeepSpeed integration. And then recently we've been looking a lot at accelerator abstraction, and so now DeepSpeed runs on a variety of accelerators, and we hope to keep growing that. So essentially, we want DeepSpeed to be available everywhere. Want sort of a DeepSpeed inside kind of message. None of this will be possible without our open source support, right? So DeepSpeed is really an open source success story. Here's a list of some shots of our contributors. We have over 300 at this moment, and I know it's growing. The DeepSpeed at any team at any point in time had always been less than 20 people. And so it's not that we don't sleep or we work around the clock or we have like super big brains. No, it's because the community has really supported us. And we've received massive amounts of PRs from both individuals and from companies. And we're very, very grateful for that. Here I just put up like in terms of the story success, we have 31,000 stars. You can make of that what you will. Over 5,000 dependencies, and we're on release 0.13 right now. And that would be the end of my talk. I will take questions if there are any. Thank you. Yes. Sure. Oh, yeah. You had to ask that question. Oh. Let me put it this way. It's in the works. It's something aspirational that it's a gap we have that we have to fix. And I recognize that. So it's mostly been Linux based right now. But yeah. Yes. NVIDIA GPUs and the AMD? You said? Okay. All right. Okay, great. Sure. Let me answer it this way. Up till, I'll say maybe early last year, we had CUDA references all over our code. Today, we don't have CUDA references all over our code. So yes, a few years ago, maybe a year or two ago, it was all sort of NVIDIA. But lately, we've sort of moved away from that, and that's because of these other vendors you're seeing here. They're interested in having DeepSpeed run on their hardware, and so we are. I think it's fair to say now we are very much abstracted away from an accelerator perspective. We can support pretty much any hardware right now. Yes, please.
My question is easy. Is there a plan to start, for example, like a Slack group or Slack channel for DeepSpeed for like better community support?
It's under consideration. By the way, my boss is here. That's why I'm asking very coyly. So you can ask me outside. What? Okay, there you go. You have an answer. Yes, it's going to happen.
Yeah, thanks for the presentation. So there was this graph a while back where you have like effective throughput and number of clients, that one right there.
Yeah.
Can you help me understand why it sort of has that curve rather than leveling off, which is maybe what I might expect?
Oh, it wouldn't level off because essentially because once the load, so we have an SLA that we need to meet, right? That's defined. And so once we, and so this is just showing the ratio of requests that are actually meeting that.
Oh, I see.
Yeah.
It's not throughput. Yeah. Like raw throughput. Okay.
Yeah. Yeah. Saka? Yes.
I could be loud. Do you do asynchronous gradient accumulation? Like, it's a technical question, more like, when you train a model and it goes through the layers, can you start like feeding the input to the earlier layers while the later layers are processing like previous batches? Do you do that at all?
So is that asynchronous? So, I mean, because that sounds a little bit like pipeline parallelism. So I'm not sure. So asynchronous would mean that
maybe I'm not an expert on the terminology here. So
I see. So well, I'll maybe the general answer is like the DeepSpeed engine itself is designed to be very simple. So you could actually implement any algorithm you want using our engine, right? So if you wanted to sort of implement like asynchronous, like you said, you could implement that using our library. So we don't actually implement like synchronous or asynchronous. It's not hard coded in there, but but you can implement whatever you want. Makes sense. I think
Okay, so this one is maybe like a bit of an out there question. So we talk a lot about like GPUs, but these days people are making all sorts of like kooky hardware accelerators, right? Um, I don't know much about DeepSpeed, but how easy it is to extend if you have a kooky hardware accelerator.
It's great. Well, so let me go back here. I would say not so bad, right? So Gaudi is, I am learning, Gaudi is a fairly kooky hardware. So the thing I learned about Gaudi fairly recently was that it actually doesn't execute any of your instructions when you run them. It's sort of a data, it resolves data dependencies on the fly. So you feel you're executing stuff, it's not doing anything. But once you try to print an output, then it kind of like catches up and executes everything out of order. And it runs with DeepSpeed. So I feel I'm not sure I can think of anything more kooky than that. Like so.
Yeah, so then I guess like a somewhat of a follow-up question. So you mentioned this thing called DeepSpeed config, and that you were
Yes.
like very proud of.
Yes.
Underneath the hood, what is the way to think of that like as a programmer? Is it kind of just like how in Hugging Face you have these KWARG arguments that just get piped and handled magically through the system? Is it somewhat analogous, or
Yeah,
is it tighter?
it is analogous, and I think it's kind of interesting. Like we work very closely with Hugging Face folks, so it's not actually clear to me whether they got the ideas from us or we got the idea from them, or it was just some kind of like just when you work with people together, you just end up thinking the same way. But yeah, it's kind of similar. Yeah, but the idea there is that we view our DeepSpeed engine as something that you can configure for your need, and we want you to be able to do that without necessarily putting things on the command line, which is sort of the other way you could go about this. Yeah. Yeah, I think we had. Yes, please. I mean, they are a big part. They're a big differentiator in terms of hardware performance, right? So for something like the AMDs, the MI100s, and the MI250s, setting communication performance is much worse than NVIDIA machines. But that is somewhat orthogonal to what we do because we're just software. So we just try to help you get the best performance that your hardware can provide you, but we don't go beyond that. Yeah. So Ray are built on us. They use DeepSpeed in the backend. Yeah. Yeah. So yeah. So I want to think of us as being quite low level in the sense that the goal for us really in DeepSpeed is we recognize that for your deep learning, you need basically three things. You need compute, you need memory, and you need communication. And we are just optimizing those. And then you can build anything on top of us. All we're just providing you is the best performance you can get from a compute perspective, from a memory perspective, from a communication perspective. And folks do build all sort of things on top of us. That's separate. We're not. Yeah. Yeah.
Hi. How do you get 30 gigabytes per second from a single NVMe device?
Not a single NVMe, from the server. So the server had 8-micron devices on it and aggregated to like 3.5 terabytes each, aggregates to 30 terabytes.
That's way more sensible.
Yeah. Thank you.
Okay, if there are more questions, we will have more social time after the presentations, and then you can ask Tunji. I think we have a few other DeepSpeed members in the audience. Can you guys all raise hand or stand up so people know who you are? Yeah, grab these guys, talk to them, ask all the questions you want about DeepSpeed.
All right. Thank you so much, everyone. Taka.
Okay, so my name is Taka Shinagawa. I'm an AI cloud solution architect from Azure team. Can you hear me? Yeah, I'm gonna present something Martin mentioned. So just, what I'd like to make sure is, okay, the guru presented DeepSpeed. So I just want to make sure, you get some concrete answer on how to get started when you get home tonight, right? you want to start using DeepSpeed tonight as soon as you get home. So yeah, just to today I gonna basically, yeah, frankly I got maybe 10-15 minutes, and that's nowhere near I can present entire workflow. So just but I'd like to give you some quick idea how to get started with Azure ML. But before getting started with Azure ML, I'd like to really emphasize DeepSpeed is vendor agnostic. So it's not tied to any specific Microsoft technology. So as you can see in this technology stack, I think the only dependency, PyTorch and GPU, essentially. So yeah, we are very curious what kind of a technology stack you're using to run DeepSpeed, and test it. And then if you have a problem, just let us know. And then so yeah. With that, I just like to just focus on Azure ML to give you some idea like how to get started. So just wondering how many people using Azure today? Okay, so yeah, so people who are already using Azure, yeah, maybe 20-30% of this audience, yeah, can skip here, but they just first go to azure.microsoft.com and then sign up, and then sign in. Once you sign up and you get to this portal.azure.com, this is a starting point. And then yeah, for this talk, I'm gonna use Azure Machine Learning, but this is very exciting time at the Microsoft for Gen AI. So we have a new product called Azure AI Studio, which contains some of the features I'm talking about. So just in the future, just watch out for AI Studio. But just in this talk, I'm gonna use Azure Machine Learning. Then Azure Machine Learning. I would just start with very easy way to use DeepSpeed. You don't have to code, just use GUI. So the easiest way is to use a feature called Model Catalog. As the name suggests, Model Catalog has lots of pre-trained models. So from GUI you can inference pre-trained models. And also you can fine tune it on the cluster through GUI. So yeah, this is how model catalog look like. So it's a little small screen, but yeah, we have a partnership with Hugging Face, Meta, Mistral, NVIDIA. So there's so many hundreds of models, both base model, fine-tunable base models, and fine-tuned models. Then just all you have to do is to pick a fine-tunable base model. So here, very most popular one today, 11 to 7 billion. So just go to the base model page, and then there's a little button link, fine tune. So all you have to do is to click, and then here you specify training or validation test data sets and the compute cluster. And then in order to use DeepSpeed, you have to click this advanced setting feature. Then here, yeah, this is a config to enable DeepSpeed. And then I'd like to definitely just emphasize, this is super important, right? So after enabling DeepSpeed, deep speed stage, right? Not much information provided here, but the guru already presented earlier. This deep stage 2 is this 0 or 0, 2 for gradient partitioning. So stage 2 allows 8x memory reduction with the same communication volume as data parallelism. So I think I would start with this for regular fine tuning. But if you're training really large model, and then, for example, you try the stage 2 first and get out of memory errors, or yeah, you may want to try stage 3. And then definitely stage 3, you get on network overhead, but you could train a really big model or bigger model with the same amount of GPU. Then just, once you start the fine tuning, just wait for it. And then once it's done, just register the model. So now you know what to do when you get home today. So yeah, so this is the easiest way. But like most developers or ML engineers, okay, we know GUI people. So we just want to train the model like using custom script. And just, I'd like to give you for people new to Azure ML, this is, setup you may want to use in Azure ML. So, Azure ML, you can, run your training script on a Docker environment. Basically, it's called a Azure ML environment, which is a simply Docker, image with all the Python packages, dependencies installed. So in order to run DeepSpeed, you need to have a DeepSpeed installed. But in order to initiate the job and configure the job, just you need a small VM, like just a CPU VM, or compute instance to launch it. Then this is how notebook environment looks like. Then just for the environment, nice thing with Azure ML is we have a pre-built environment, Docker image called Azure Container for PyTorch. So with that, you don't have to spend any time installing DeepSpeed. So you just use this pre-built environment. And then sometimes I need extra Python packages. In that case, I just built a new Docker image based upon this Docker image. And then also, Tanji, like this DeepSpeed is optimized, right? Right. So I highly recommend using this environment if you're using a DeepSpeed on Azure ML. So, and then actually, like I like to, there are lots of, DeepSpeed, supported libraries. And then in reality, I use Hugging Face Transformer or DeepSpeed plugin quite a bit. And then, DeepSpeed or PyTorch Lightning is also popular. And also Hugging Face has another library called Accelerate, which has another DeepSpeed plugin. So yeah, definitely if you guys, trying out these, libraries, or let us know how it works. And then, I'm very curious to know, like, if they're working very nicely or having some problems, or yeah. Then just, this is very important. So because fine tuning is very, I do believe it's the most popular use case of using DeepSpeed today among commercial customers or users. And many people want to train their own, fine-tune their own model using RLHF technique. And then DeepSpeed chat is the best library on the planet to fine-tune with RLHF today. One reason is that actually the biggest reason is in RLHF, step 3 is the most resource-intensive step, right? And then, you don't want to implement that from scratch. Yeah, you have to, like it's gonna take a very long time. And then also, the secret weapon behind this DeepSpeed chat is this DeepSpeed hybrid engine. So because this hybrid engine is actually running behind the scenes, step 3 for reinforcement learning step, where multiple models need to be loaded, and then training and the inferencing has to happen simultaneously. Yeah, this hybrid engine is making the huge difference. So this is really, really helpful for RLH fine tuning. And then, yeah, just to get started with this speed chart, just go to, clone this repo, get to the deep speed chart directory, and then there's some sample scripts already available. So it's pretty easy. So you know what to do tonight. So yeah. Then just, don't forget to finally, just, I'm done with fine tuning talk. And just before closing this talk, yeah, don't forget to try out DeepSpeed fast gen. It's very easy. In the Tanji's slide, this pip install, this speed MI was missing. So it's very important, but it's very easy to get started. And then just finally, we're planning to do more meetups in the future. So please join this public meetup. We're gonna announce lots of stuff in the future. So yeah, that's all for my talk.
Any questions? This is actually the public meetup. Yeah, this is, yeah. It's just, I think. Oh no, I mean, that's the group Taka wants everyone to join to stay informed of additional meetup events, because this is our first ever meetup. So the content we presented is more of an overview rather than a very deep dive of a specific topic. But going forward, as we do this more regularly, we want to have like each meetup to focus on something, a very specific topic, and we'll be communicating those over Meetup, so people can see those information. Okay, if no more questions, I think there's more time for more pizza, more. How frequently, Tonji? How frequently do you want to come over here? Oh, by the way, Tonji is based in Knoxville. That's East Coast. So.
We're thinking once a quarter. So we're thinking once a quarter at this time, and but if you guys ask really hard, maybe we'll do one every month. Online meetups?
Yeah. Yeah, actually, I'm based in Bay Area, San Francisco, so I'm planning to have a DeepSpeed meetup in San Fran. So just, if anyone here is interested in, yeah, DeepSpeed in Bay Area, let me know. And then also anyone like, who wants to host this meetup or present in the future meetup, yeah, we're open to it.
So at the beginning of the presentations, we thanked Yuxiong for starting DeepSpeed. Now, at the end of the presentation, we want to thank our new boss, Misha, here, for continuing to support our open source effort for DeepSpeed. Really appreciate it. And thanks for coming today.